Okay, so today we're going to do a new level in the operating system. We've been toiling away in binary and hex at the machine language level at HOL, no, we've been at what level? ISA 3. We've been at ISA 3. And today we're going to jump up 2 levels from ISA 3 to ASMB 5. So this is chapter 5, and the topic is assembly language. And so here are the 7 levels of abstraction in a typical computer system, and we have been down here at level 3, instruction set architecture level, and now we're going to go up to level 5, which is the assembly level. Now, so there's a little story about this. What happened was, in the very early days, the computer programmers didn't want to have to write all their code in binary. So what they did is they invented a little shorthand language called assembly language that was more convenient for them to program in. And then what they did is they hired a clerk. They hired a room full of clerks, and they would write their programs in this assembly language, which was more convenient for them to write, so that they wouldn't have to like memorize the opcodes and memorize the addressing modes and all that kind of stuff in binary. And then they would give those programs in assembly language to the clerks, and they would do they would look up and do the translation into machine language, and then they would hand it over to the machine operators, and they would put it in the machine and run the program. So what we're going to do now, so let's just think about that historical evolution about the way of how computers evolved, okay? So now, what we're going to do then is we're going to describe the PEP9 assembly language, and the purpose is to make it more human readable, make it more convenient for us to program so that we don't have to program in binary and in hex anymore. But we have to remember what happens is this is a strict translation from, there's a strict translation from assembly language to machine language, okay? So what we learned about all the instruction sets and all that information representation in binary using 2's complement binary representation, all that stuff still applies. This is just making it so that it's easier to write programs so that we don't have to write them in binary. Okay, so here's how it's going to work. Recall that there are 2 types of bit patterns when we write a program. There are instructions and there are data. So for example, when you wrote your program to print out the letters of your name, the letters of your name were the data, and the instructions to do the load byte and to store the byte to the output device, those were the instructions. So there's 2 different kinds of bit patterns in a machine language program: data, instructions, and data. And so we have a different assembly language constructs to handle each one of those kinds of bit patterns. So first of all, for the instructions, what we do is we use mnemonics for opcodes and letters for the addressing modes. Now, what is a mnemonic? M-N-E-M-O-N-I-C-S. What is a mnemonic? Yeah, like every good boy does fine, that's a mnemonic.
Something that helps you remember something?
Yeah, it's every good boy does fine is E, G, B, D, F. You know what that is? That's on those are the notes on the lines, right? And what are the notes on the spaces? Face. So you can remember face, that's a mnemonic. It helps you to remember F-A-C-E. Right? So what we're going to do is we're going to have a set of mnemonics for the opcodes, and then we're going to use letters for the addressing modes. So here in figure 5.1 are the letters that we're going to use for the addressing modes. Okay? So you remember there's the addressing AAA field. And so there are 8, because there are 3 bits for the addressing field. How many values can 3 bits hold? 2 to the 3, which is 8. So these are the 8 addressing modes. And starting from 0000, which is immediate, all the way down to 111, which is stack deferred indexed. What we do is we have letters for them. So I is for immediate addressing, D is for direct addressing, N for indirect, S for stack relative, SF for stack relative deferred, X for indexed, SX for stack indexed, and SFX for stack deferred indexed. So, which addressing mode do we have we learned? Have we used all so far? Direct. So our letter is what? D, little lowercase d. All right? So now here in figure 5.2 now are the mnemonics. So you see the column that's labeled instruction specifier, that's what we had before, right? We have the opcode, or the first few bits, and then we might have a register R field, or an addressing A field, or an addressing AAA field. Okay, so that instruction specifier column is just like what we had before. Here, if we look through the whole table, you see that it's just like what we had before. All right? But now what we're going to do is we are going to associate with each one of those instructions a mnemonic. And so the mnemonics are stop, ret, return, RETTR, and so on. Okay? And then, so let's take a look at some of the at some of the instructions that we already know. Stop, you see, so now instead of writing 00, we can write what? Stop. Okay, and then the assembler is responsible for translating the word stop into 00. Does everybody see how that works? Okay, and what were some of those other ones? Let's go up here to this part of the figure. Do you see this LDWR? That stands for what? Load word. So there's two versions of it because it says LDWR. So that could either be LDWA or LDWX. Are you with me? This is how to write those two versions of the load word. And do you see what the opcode would be? The LDWA would be what? 1100 what? 1100 and then 0, and then if it were direct addressing 001. Are you with me? And then LDWX would be what? 1100 1001. So everybody, are you with me on that? Do you see how to write those? Okay. And then the one that we used a lot for outputting characters, there's a LDB, there's an LDBW, and an there's an LDBA, there's a load byte accumulator, and then there is a load word, and then there is a load byte index register. Okay, does everybody see how to write those in assembly language for the mnemonic? All right. Yeah, question?
The A is for the accumulator and the X is for the load index.
Yeah, this means load word accumulator, and because it's load word accumulator, this register R field is a 0, and this is load word index register, and because it's the index register, this R bit is 1. Do you see how that worked? Yeah. Okay. So we have these mnemonics, so now we don't have to, mess around with, hex and binary. We can write these meaningful words in our programming language. Okay. Let's go back to this level diagram of our system. What we were in at level ISA 3, instruction set architecture level 3, now we are at what level? 5. So what's in between? The operating system. So now what we're going to do is we are going to take advantage of the services provided by the operating system. So So what we're going to do is we're going to have some new instructions that the operating system is going to provide for us. Okay? And do you remember how last time we talked about how difficult it would be to output a a decimal value that had 2 digits in it? Well, check this out, sports fans. This set of instructions now, these are called trap instructions. And what happens is, when you execute one of these an opcode that is a trap opcode, what it does is it automatically behind the scenes jumps to the operating system, and the operating system has a series of statements that executes to implement that one instruction. So look at this one that was going to help us with that previous problem. Decimal output trap. So what happens is, this decimal output solves that problem of having a more than 1-digit numeric result that we want to output. So if you have like a 13 and it's in binary, it's written in 13, and you do decimal output that number, and what will come out will be a 1 and a 3 as it needs to be, as it needs to come out. Okay? So these instructions, these set of instructions, we have decimal input, decimal output, hexadecimal output, and string output. These are all provided by the operating system, because now we are above the operating system in our levels of abstraction, you see. So the operating system can provide these services for us. Yeah?
So why do these need to be done in the operating system, but then like there's those other commands that aren't?
Yeah, that's a really good question. Because the hardware, those other commands are literally wired into the electronics of the CPU in the hardware.
Okay.
You see, these instructions, this decimal input and decimal output, these cannot be, no hardware CPU has at the hardware level instructions that do what these instructions do. So they have to be provided by software in the operating system.
Okay.
That was a good question. Does everybody see the story here? I mean, what's going on here? Okay. So now that's how, so the mnemonics and with the letters for the addressing mode, that's how you write an instruction. Now, the other kind of information that's stored in a machine language program is data. Now with data, there is no like opcode, there is no, addressing AAA field. Like when you're storing the letters of your name, or when we're storing the number 5 plus the number 3, and we have the 5 and the 3. Well, the 5 and 3, there's no opcode associated with that. So these bits are generated by what are called pseudo-ops, pseudo-operations, also called pseudo-ops. And pseudo-ops always begin with a period. All assembly languages, they have pseudo-ops that start with period. And so they're also called dot commands because they start with periods. Okay, and pseudo, what does pseudo mean? Fake. So it's like fake operations. They're not really, they don't have opcodes. So they're pseudo-ops, because they don't have opcodes. And we're going to learn most of these in the course of our studies. The ones that we're going to use right off the bat here are dot end. So what do you have to put at the end of the loader in order, as a sentinel for the loader? What do you have to put? ZZ. So that dot end corresponds to the ZZ. Okay. So you just write. Now you can write dot end, and then and the other one that we're going to look at is the dot ASCII command, which will let us put the ASCII characters in our program without having to look up the ASCII chart. It'll do it for us automatically. Does everybody see how that works, or what the deal is? So now what let's do is let's take a look at figure 5.3 at a program that outputs the word hi that we did in machine language, and here we're doing it in assembly language. So check this out, you guys. First of all, in assembly language, what do you see up there at the top? How do you write a comment in assembly language? Semicolon. Anything after semicolon is ignored. Are we good? So obviously that's where you put your name, the date, and the assignment number when you hand in your assembly language programs. Okay. And now let's take a look at that first one. That first one is load byte accumulator. And look at how we write it. We put 0x000D. Now, why do we put 0x? What was that 000D?
It's hex.
Yeah, that's where the H is going to be stored. That's going to be the address of the letter H. Are you with me?
Or that's where it's storing the H, or that's where it's getting the H from?
That's where it's getting the H from, because the H is stored at 000D. Just like, so you would like have to count it up like we did before. Although I'll show you in a minute, there's a really slick way to find out where it's stored. Okay, so this is load byte accumulator from 0x00, and then we do, and now do you see we do comma D? So what is that comma D? That's direct addressing. So now we just say comma D. So we just say direct addressing. All right, and then the next one is what? Store byte accumulator to where? 0x what? FC16. What is FC? Does that sound familiar? FC16?
That's correct. Yeah.
That's where the output device is wired into. Okay, so what is that called? What kind of I/O is that called? That's memory mapped I/O. Okay, so that's where the output device is stored. And it's also direct addressing. Okay, and then what's the next one? Load byte accumulator 0x000E. That's where the I is stored. And then store byte accumulator 0xFC16D. And then stop. And now look, you guys, you don't have to look up on the ASCII chart to put the hex for the letter H and the hex for the letter I. You can use this, what is this called? .ASCII. That is a dot command or a pseudo op. And you can just say .ASCII and you put in double quotes whatever you want. You just put whatever letters you want in there, boom. And the assembler will actually convert that to the proper hex for the machine language program. Is that neat? Right? And then .in, that corresponds to the ZZ. And if you run, if we put this program in the, if we write this program in assembly language and invoke the assembler, then what it'll do is it will produce this output. And what does this output look like? D1000D, F1, FC16. You see? there it is. It translates it from here to here. Now do you see, what could happen is you could do this. If I, and in fact you will, if I give you an assembly language program, I will ask you to do this over and over again. You need to know how to translate from the assembly language to the machine language. But it's easy to do with all those tables. Right? It's all just a mechanical process. And here, in this next figure, shows what the assembler does. Okay? So what it does is you write the program at level ASMB 5, and the assembler translates it to machine language. Are you with me?
So it skips forward.
Well, yeah. It uses, yeah, that's a little, what happens is level 4 is what lets us use those trap instructions. So even though it's running at level, yeah.
So it's kind of like written at level 4 and 5.
Yeah, it kind of is. It kind of is. The operating system has already been written and is installed in the PEP9 virtual machine. So when we use the deso instruction for decimal output, we will be invoking that code that was already written that's installed in the PEP9 virtual machine. Yeah, question?
Were assembly levels, was the assembly level developed before operating system level was?
Yes. The question is, was the assembly level developed before operating systems? The answer is yes. It was very early on, because see what they did, because look, actually, here, watch this. Actually, you should know this. We're going to talk about this a lot later on, but we might as well bring it up now that we're talking about assembling. The fundamental, do you know what, did you know that computer science has a fundamental question? And do you know what that question is? What is the fundamental question of computer science? There is.
That is my question.
It's what can be automated? What can be automated? That's the fundamental question of computer science. Because look, and so this gets back to your question of which was developed first. What happened was, these assembly languages, and they're I'm talking about really, really early, you know, like very first electronic computers. It was all done by hand, and the programmers wrote those the assembly language programs. Of course, it wasn't PEP 9, it was the early machines, but they wrote the assembly language programs by hand. Then they turned them over to the clerks. And the clerks had the opcodes and the addressing modes, and they converted them to binary, you see. And then the binary went to the machine operators, and then they loaded them in the computer and ran the job. So at first, assembly language was translated manually. But now, what's the fundamental of computer science? Fundamental question of computer science? What can be automated? So eventually, somebody figured out what? At one point in time, somebody figured out that what? And yeah, they say, oh, you know what? I can write a program to do the translation. And so now what happened to all those assemblers? Out of work. But I'm telling you guys, that is what we do as computer scientists, because this is the fundamental question of computer science. Our job is to put people out of work. Literally, so this is really a huge economic point that we are directly involved in as computer science people, because our job is to automate. And when you automate, what do? What happens? You automate something, what happens? Somebody loses a job. You need to think about this. We need to think about this but clearly, how does that benefit society? I mean, if we didn't automate, where would we be? I mean, what about all those people who lost their jobs, in the, manual labor, before machinery came along, okay? So you don't be a Luddite. You have to understand economics if you're a computer scientist, because what can be out? Think about it. Facial recognition, all this stuff. A human can recognize a face. Well, maybe a computer program can recognize a face. So we don't need humans to recognize faces. You see what I'm saying? So yeah, it's something that we should be economically literate, especially we should be, because that's the fundamental question of computer science, is what can be automated. So now with the PEP 9 app, what it does is it actually does it automates the translation. It does the translation. I'll show you in a minute. And so here is a visual, this in figure 5.5, here's a visual depiction of exactly what the assembler does. Now, do you remember that every computation, there's 3 parts to every computation. What are they? Input, processing, and output. Now, do you remember that little figure from before? Input, processing, and output. So here it is, what an assembler does. What is the input to the assembler? It is a what? What is that input there? It is a what? Yeah, what kind of a program written in what language? It is an assembly language program. Are you with me? It is an assembly language program. And then the assembler takes that as input, and does it execute that assembly language program? Yes or no? No, it doesn't execute it. What does it do? It translates it to D100. Instead, it translates LDBA space 0x000D comma D to what? Yeah, D1000D. That's what it does. Now, does everybody see what that does? Yeah.
So is the D1000D and the real binary all considered part of ISA?
You should recognize D1000D as a machine language statement. And if you decode the D and the 1, and you look at the opcode and the register R field and the addressing mode, you should recognize that as the load byte accumulator, as the load byte instruction where the register R bit is the accumulator. That's what it is. So that is all looped inside the ISA3, and then microcode is something below that? Okay. Yes. Okay. Oh, I see what you're saying. Yeah. The output in figure 5.5 is a level ISA3 program. In fact, it is the same program as what's in the input, but it's written in machine language instead of being written in assembly language, and the assembler translated it. It's the output of the assembler. Now, this is really crucial, you guys. We really have to understand these details. Yeah, question?
So I know before you told us that machine language it's different for each operating system. Is assembly language universal?
No, that's a good question. So the question is assembly language universal? And the answer is no. The assembly language is directly tied to the level ISA 3. For every statement, for every instruction, assembly language instruction, there is exactly one machine language instruction. It is a one-to-one correspondence. That was a good question. Unlike high-level languages that are machine independent.
Okay.
Yeah, that was a really good question. Yeah.
In the assembly language, is the 0x, like, is that just a standard, or is there something that's...
Oh, that's a good question. Now, here's the thing. In all assembly languages, even in C and C++, the way you write a constant in hexadecimal is to prefix it with the character 0x. Are you with me? So that is an assembly language notation. Very common. It's industry standard. So when you see, because look, what about the number like 07? Is that 07 decimal or is that 07 hex? How would you know? Well, you prefix it 0x07. That tells you that's a hexadecimal 7. You see how that works?
Yes.
That's a very common convention, and that's what we have in this. Are we good? Okay, now you guys, then let's take a look at, it was figure 5.3. Now let's do a little demo and see how you could run figure 5.3 in assembly language. Okay, so here's our demo, and what we're going to do is we're going to take a look at program 5.3. Now, what we could do is we could write, you know, semicolon, name. I could just type all this stuff in, right? But our app has a nice little feature here, figure 5.3. Did you see how we went to the help system? And we can do copy to source. Don't save the changes. Okay, so here we are, and this is what you would type, right? Does everybody see that? Here, so this is load byte accumulator 0x000D, store byte accumulator 0xFC16. So this is what we saw in the figure, right? Now, I'll tell you what let's do. Let's suppose that we typed this, and that as we typed it, we made a mistake. Like, let's just put some crazy letters here. All right, and so as we were typing this, we made some errors. Let's see what happens if you make some errors. If we do a build here, watch what happens. See here? Error, invalid mnemonic. See? So we got to make it correct. Yeah, question?
Does it know, like, do you have like a tab between those parts, or is this? Yeah,
that's a good question. Tabs are good. This has smart tabs actually. I can demo this by making it kind of flaky here. And oh, and by the way, if you want to, you can go up here to under edit, and you can do remove error messages if you want to get rid of that error message. But if you don't want to remove it, that's fine. That happens automatically the next time you try to do a build. So here if we do a build, see it worked. All right, now look, when it does a build, what it does is it gives you two things. You see, here's the translation. It put it in this object code pane. But another thing that it gives you is an assembler listing. And this assembler listing has everything all formatted very nicely. The addresses are here, and then here it shows you, what does this column say? Object code. So you see here you see how this is D1000D? Well, this is D1000D. Well, this is how the loader requires it. This is for our own personal inspection. Are you with me? And by the way, you guys, what do you see it did with this .ASCII? Hi. It made the what? The 48 here and the 69 here. And look, what did it put right here? 000D. So now you can see, once you do a build, you can see where your data is going to be stored at the bottom of the program. And then you can go back and you can just put a dummy value there, and you can go back up here and fill it in. And there's another, and here's, I really want you to do this. There's another feature that you need to do before you hand in every program. Once you do a build, come up here to Edit and do Format from Listing. What this does is it takes this code from this column on to the end with this listing, And if you do format from listing, it prettifies this. Do you see? So you should do that. You should do that. You need to do that before you hand in. Don't hand in stuff all in wacko format. Okay, is everybody clear on that? All right. And so now, and here as before, we can, if we run the source, it will assemble and run it, and so there's the high. But now look, here's another cool thing about assembly language. What we could do is, we could take a look at this memory dump. We could go to System and Clear Memory, and we could, just like we did before, we could go to Start Debugging Object, and we could single step through this, boom, 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 and there's the H and there's the I. Are you with me? So we could do that. That's still available to us. But there's another cool feature here, and that is, so let's clear the memory. And now let's, instead of doing Start Debugging Object, let's do Start Debugging Source. Now watch this. If we do Start Debugging Source, this little button does the same thing. Start Debugging Source, watch this. Now you see what it's doing is, here we don't, it's tracing through the source one step at a time. So boom, 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 boom. And see, and it's doing it at the memory dump too. But at the assembly language level, you usually don't need the memory dump. You can just start debugging source, and you can single step through the source, and it shows you what's in the accumulator and the CPU, and boom, boom. See, and you just switch between the trace and the code like that. Yeah, question?
When it starts doing the trait, like the troubleshooting with this, does it pull from like the object code or from the source code?
That's a good question. What has to happen is you have to do a build, and it pulls it from the object code, but it knows the source code that it came from.
Okay.
So it's actually executing, when it's tracing, it's actually executing the object code.
Okay.
Yeah. Does everybody see how that works? I think that's all for this demo. Okay, so that's figure 5.3. Now let's do another one. Here is the program, figure 5.6, that takes two letters from the input device and outputs them in the opposite order. So does everybody see how this works? The instructions in assembly language are load byte accumulator from 0x in hexadecimal, in other words, FC15, so that's the input device. Are you with me? Direct addressing, comma D, and then store the first character, so store byte accumulator, and then load byte accumulator, and then store byte accumulator, load byte accumulator, store byte accumulator, stop, and there it is. Now, we have a new pseudo op here, that's the dot block 1. Okay, so here's what dot block does. Dot block n generates n bytes of all zeros. Generates n bytes of all zeros. That's what dot block does.
Why
So
would you need that?
yeah, for storing, to allocate storage. Yeah, we'll see. We'll see how it gets used later, but that's what it does. And in this particular example, we just want to indicate where that first character is going to be stored. So we say dot block 1, and it generates 1 byte of storage. Okay, is everybody with me on this program? And here is that program to add two numbers, the 5 and the 3. So now, what is the first instruction in this program? Load what?
Word accumulator.
Load word accumulator. How many bytes is a word? 2 bytes in a word, because our accumulator is 2 bytes long. So all of our arithmetic is done in, this is a 16-bit machine. All right? Is everybody good? So we load word accumulator from what address, from what location? 000D, using direct addressing. And then add accumulator. Additions, there is no such thing as an add byte. We always add, so it's just, we always add 2 bytes. So it's just add. is the mnemonic. And then OR accumulator, that's the mask. Does everybody see how that works? Okay, that's to convert to the ASCII. And then output the character, store byte accumulator to the output device at FC16 using direct addressing, and then stop. And now look, now how do we put that 5 there? Dot word 5. Okay, so now dot word, see dot block, n generates n bytes of all zeros. What do you suppose how many bytes does dot word always generate? 2. So let's note that. Dot word always generates 2 bytes. And look at what we have for dot word. When it says dot word 5, what bytes does what does that generate? 0, 5. In hex. Are you with? Wait, no, is that right? No, 0005 in hex. Right? 2 bytes. Is that right? Dot word always generates 2 bytes. So that would generate 0005. Is everybody 0005? And then the dot word 3 generates how many bytes? Always 2 bytes. And the dot word 0x003 generates how many bytes? 2. And do you see then that we can tell the dot word whether to generate, we can give it a hex value or a decimal value, and it will generate it accordingly. Does everybody see how that works? And then stop, and then, well, stop, and then the dot words, and then the dot end. And the dot end is what puts the ZZ on the end. Okay? So now, figure 5.8 is a crucial figure. Because what has to happen is when you write a program in assembly language, it cannot be executed directly. It has to be translated first, then executed. Now, what are the 3 activities of all computations? We have input, processing, and output. So what has to happen when you run an assembly language program? First, you have to translate it from assembly language to machine language. So do you see that the input is your assembly language app? It's a program written in assembly language. The processing that's done with the assembler is to convert that to machine language, the object program in machine language, and then that object program is what gets loaded into the computer and executed for the second run. Now here is a really crucial point. All programs, in order to be executed, have to be written in what? All programs that execute must be what? Must be in what language? Because what does the von Neumann cycle do? Fetch, decode, increment, execute, repeat. So all programs that execute have to be written in what? Machine language. All programs that execute must be in what? In machine language. Now, do you realize what that means? That means that first step, that assembler, what program is executing in that first step there? What? That's the translate. Well, so what language is the translator written in? That has to be the machine language version of the translator. Do you see? That is crucial because look, we know what a von Neumann machine does. It does fetch, decode, increment, execute, repeat. It expects that stuff in binary. That means that the translator itself has to be in what? machine language in order to execute, in order to do the translation. Now look, this is crucial. This is a big idea. You see what's going on here? Yeah.
When you say translator, do you mean the assembler?
Yes, the assembler is a translator. But the assembler itself, in order to execute, to do the translation, the assembler itself must be in what? Language. Machine language. Now, this is a crucial idea in computer systems, yeah.
So how is it that with like 2 digits, how is it that the operating system can handle that if the operating system has to be translated into like 1s and 0s?
That is a really good question. In fact, that is such a good, the question is, how does that decimal output with the 2 digits thing get translated, blah, blah, blah. I'll tell you what let's do. Let's start off next time with a demo to show you that question, because that's a good question, and it'll take me a little bit of time to demo it. So let's start off the class next time with that demo. Remind me.
Okay.
I should remember anyway. All right, good deal. See you guys next time.